Now we look at the centripetal force equation. And we start by reminding ourselves about centripetal acceleration, which was covered in our earlier video. This is the acceleration necessary to stay in circular motion. It must point towards the center of the circle. That means it's center-seeking. That's what centripetal stands for. And the equation that we ended up deriving for this in the previous video was AC, the centripetal acceleration, was equal to v squared over r, where it depended on how fast it was moving, the v, and how tight of a turn it was, the radius. So that leads us to centripetal force, the force needed to stay in circular motion. And think of it this way: if that force went away, the object would not continue moving in a circle, it would move off in a straight line. And like any force, it's going to be a mass times an acceleration. In this case, since it's a centripetal force, it's a mass times a centripetal acceleration. But we know what that centripetal acceleration should be. We saw that in our review slide just a moment ago, that it's v squared over r. So that means my centripetal force is mv squared over r. And the equation then tells us that the force is equal to the mass. I've got my radius on the bottom and my velocity squared on top. Now I can take a look at the units for these quantities. Mass has a standard unit of kilograms, radius has a standard unit of meters, and velocity has a standard unit of meters per second. Putting this all together and remembering that my velocity is squared, I've got kilograms, meter per second squared, over a meter. Now, there's quite a bit of algebra I can do in here, particularly with this meters per second squared. If I do all that algebra, I'll see that I've got kilogram meter per second squared. And that's also known as a Newton, which is the unit for any other type of force. So centripetal force is measured in units of newtons just like any other force. So that's our introduction to centripetal force.